Welcome to homework.
Hello everyone, today we're doing chapter 14, problem 24. And this problem gives us this NMR spectra and a molecular formula of C3H8O. And it tells us that we have an IR absorption from 32 to 3600. And it asks us to propose a structure for this molecule using these information that was given to us. So the first thing that I like to do is to determine what this IR absorption peak can possibly be, what functional group particularly can this be, and second, determine the number of double bonds or the degree of saturation. So this equation I wrote here, it's a trick that I used when I was a student, and it helped me to identify the degree of saturation or number of double bonds. They're synonymous. So your degree of saturation or the number of double bonds equals the number of carbons minus the number of hydrogens and halides over 2 minus the number of nitrogens over 2 plus 1. So this plus 1 is just accounts for like any and all oxygens in your molecular formula. It doesn't matter if your formula does not have an oxygen, you still have to do that plus 1. So if we follow this equation, we have number of carbons equals 3 minus the number of halides and hydrogens. So we have 8 hydrogens and 0 halides. So we have 8 over 2 minus number of nitrogens over 2. You have 0 nitrogens over 2, so that's 0 plus 1. So that gives us 3 minus 4 plus 1. So that equals 0. So we have 0 double bonds or 0 degrees of unsaturation. And now if I look at my IR chart in the textbook, I see that a strong peak between these two values is most indicative of an OH bond. So now that we know the O here in the molecule is going to be involved in an alcohol bond right here, and now we have 3 carbons. So we have 1 carbon here. Obviously, it's going to be bound to this oxygen, and we don't know where the other 2 carbons are. We don't know if it's going to be a straight chain alkane or if it's going to be some sort of geminal group here or what it's going to be. But now we have to look at our NMR spectra to figure that out. So let's go from right to left. So from most upfield to most downfield. So this doublet here at around 1.2 represents 6 hydrogens. And these hydrogens are splitted by 1 neighbor. So we know it's 1 neighbor because n plus 1 gives us the number of peaks. So we have 2 peaks. So if I do 2 minus 1, that gives me the n. So neighboring equals 1. So that means that these 6 hydrogens are neighbored by 1 hydrogen. So I know that a terminal methyl group here has 3 protons. But I know that if I have another terminal methyl group here that also has 3 protons. So these two groups here are equivalent, and these would all give me the 6 protons here. And now if I'm neighbored with a carbon that only has 1 proton here, then my neighboring would equal 1, and I'll get a doublet, something like this. So this is a possible route that we can approach, but now let's confirm this route. So now we have 1 proton. Supposedly it's going to be this proton here that we're investigating. So this 1 proton is splitted by nothing. So it has 0 neighbors. But this proton here, its neighbors is 6 protons. So we would expect 6 plus 1 equals 7 peaks. So we know that this identity does not equal this proton. So now let's move on. So we also have another 1 proton here. And if we count the peaks, 1, 2, 3, 4, 5, 6, 7. So indeed, our n plus 1 equals 7. So if I do 7 minus 1, that gives me n equals 6. So I should have 6 neighbors for this proton. And this proton indeed does have 6 neighbors. So we know that this single proton corresponds to this one here. Well, what about this last proton that we're investigating? Well, if I look at my IR, I know that OH, there's an OH functional group in my molecule here. And we know that hydrogens off of oxygens or nitrogens do not split. So this can explain the lack of splitting observed here. So we can correspond this proton, this 1 proton, to the alcohol proton. And we know that now we have 3 more carbons. So if I add this group that I drew here off the central carbon, now we have 1, 2, 3 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 hydrogens, and we have 1 oxygen. So the molecular formula using this structure is true. And we know that these 6 protons have 1 neighbor, so it should be a doublet. And that's what we have here. We have a doublet for 6 protons. And this one central proton has 6 neighbors, so we should have a septet. And that's what we have here. We have 7 peaks representing 1 proton. And this oxygen's proton is not split by anything, so we have a singlet here. This is exactly what we have. So we know that this is a suggested or proposed structure for the molecular formula given, the IR peaks given, and the NMR spectra given here.